the initial position of something, or the initial value of anything, is where it starts out. During some motion or some change in something, where does the quantity start? So the initial position, where does it start? And then the final position, that means where does it end up? Where does it finally, what's the place where it ends? Doesn't necessarily stop. It doesn't have to stop there. It could keep moving. But just for our particular time interval in question, where does it end up? So where does it start and where does it end? So what we're doing here is calculating the final or ending value minus the initial or beginning value. Now let's see if this makes sense. Let's imagine that I start out the day with $10 in my pocket, and I end up the day with $15 in my pocket. What is the change in the amount of money that I have in my pocket? What's the change if I start with 10 and I end up with 15? Well, if we use this, the change in the amount of money would be the final value minus the initial value. So that would be 15 minus 10, which would be 5. So the change in my amount of money is $5. Well, that makes sense. You start with 10, you end with 15. The change in the amount is 5, going from 10 to 15. So the idea of just taking the final value minus the initial value as the change in a quantity, that kind of makes sense. Okay, so we will define now what is this? What is delta x? This is the displacement. So what does the displacement mean? It means the change in position. Now notice this does not mean the same thing as the distance traveled. We might go from 1 meter to start out at 1 meter, end up at 3 meters. The displacement would be 3 minus 1, or 2 meters. But that does not necessarily mean that's the distance traveled, because we might walk to 2, go back to -1, come to 0, come to -2, and then end up at 3. So the distance traveled in that case would be much more than 2 meters. But the displacement only depends on the initial value and the final value, which in this case would be 3 and 1. 3 minus 1 is 2 meters. The displacement is 2 meters. The change in the position is 2 meters. Okay. Now, let's notice that if our change in position is positive, in other words, if xf is greater than xi, then the velocity will be greater than 0. It will be positive. So if our final position is to the right of the initial position, we have a positive velocity. That means, now, to be precise, let's come back here for a second. What this is telling us is not the velocity that the object has at any particular point in its motion. This is giving us an average velocity. So actually, I'm going to say this is an, whoops, not B, I'm going to call this an average. An average velocity. It's telling us the velocity over this entire time interval, an average over that time interval. So if xf is greater than xi, in other words, the final position is to the right of the initial position, the average velocity, and I'll just emphasize that, sub AV, the average velocity is positive, meaning motion to the right. That does not mean that all the motion, the whole time, was to the right, because remember, the object could have gone back to the left and all the way around and ended up at 3 meters. But the average velocity indicates an overall average motion to the right. If xf is less than xi, then what does that mean? That means the final position is to the left of the initial position. And in that case, this will be a negative quantity, which means the average velocity, I switched colors there, is less than 0, which means an overall average motion to the left. And then one more. If xf equals xi. So in other words, wherever we start out, we might move around however we want to move around. But if we end up, after our total time interval, back where we started, so that xf equals xi, then the average velocity is what? Well, what's xf minus xi? If they're equal, it's 0. So we end up 0. No net or average motion. Okay? Very, very good. So we can define our average velocity in terms of the displacement, which is the change in the position, or just change in x in this case, which will be the final position, x minus the initial position. Now let's think one more thing. What are the units of this going to be? We're going to be talking about units fairly often, and there's a symbol that I will use, and that is to put something into square brackets. Anytime I put something like that, a variable into square brackets, what I mean is, what are the units of this quantity? So, what are the units of average velocity? Well, it's going to be, and this is average velocity. I wrote this out. Let me write this. V sub AB. It'll be the units of delta x divided by, the units of delta t, which will be, what are the units of position? Units of position are meters. And what are the units of delta t? Well, the standard SI units, I mean, are seconds. So the units of average velocity are meters per second. Now this is a combination of our standard SI units. The standard fundamental SI units. So remember, meters are the standard fundamental unit of distance. Seconds, the standard fundamental unit of time. Well, we've now made a combination of these. We have put together meters and seconds to make a new unit for a different quantity, velocity. So the standard SI unit will be meters per second. The standard SI unit that will be associated with any quantity that we run into will always be then a combination of the fundamental units, meters, seconds, and then later on we'll see also kilograms. So here we've got meters and seconds, and that will be the standard SI unit for our average velocity, and then also velocity, as we'll see. Okay, great. Let's imagine we make a graph of the time of the object and the position of the object along that one-dimensional axis. Now, as time goes forward, the object is constantly progressing along this axis, 1 second, 2 seconds, 3 seconds, 4 seconds. And this is showing us what the motion looks like in x. What are the x values? So here, as t increases, we see that x is increasing here, so this would be motion to the right, and then over here x is decreasing as time goes on, so that would be then motion to the left, as we'll see. Okay, very good. So we've got this graphical interpretation of what the motion looks like. Let's see how we would define what this quantity of average velocity and displacement are. Let's pick two positions on our motion. So let's pick at some initial time t1, where our object is at some position x1, and then some time later t2, where our object is at a position x2. The displacement x2 minus x1 will then give us this distance right here. That's delta x, which is x2 minus x1. So the displacement is whatever this distance is here. Or if x2 were actually below, in other words, lower down or to the left of x1, then we'd get a negative value. But just for the moment, let's just assume that the net motion is to the right, positive. The time interval, t2 minus t1, will then be this time interval here, that distance there. That's delta t, not a distance really, physical distance, a time distance. So delta t is t2 minus t1. So whatever this time is minus this time will give us the time in between. Now, what do we mean by the average velocity? What is v average? Well, v average we already wrote was delta x over delta t. Whoops, sorry, over delta t. But what does that mean? Well, if we look here, we see that this distance is delta x, and this distance is delta t. On our graph, what is delta x over delta t? Well, that looks kind of like what we might think of as rise over run. For these 2 points, the average velocity, delta x over delta t, gives us the rise over run of this little line that connects the 2 points. In other words, it's the slope of that line segment. So the average velocity is the slope of the line joining the 2 points. All right, very interesting. The average velocity gives us the slope of the line segment that joins our initial point to our final point. Okay, very, very interesting. Now let's notice, if we change t2, imagine we move t2 back this way, closer to t1, what happens? Well, as we move t2, our point then moves along the curve this way. And what will happen is the line segment, this line segment here, keeps moving down this way, and as this point gets closer and closer, the line segment that we're going to be determining the slope gets closer and closer and closer to the line that lies right along our curve. In other words, as delta t gets smaller, the slope gets closer and closer to the slope of the tangent line on the curve. Let's think about what that might mean. If you're driving in a car and you look at the speedometer, and let's say the speedometer says 30 miles per hour, what is that telling you? It's telling you how fast you are traveling at that instant. It's not telling you an average speed or an average velocity from now until an hour later or 5 minutes later or 1 minute later or 15 seconds later. It's telling you how fast you're traveling at that instant. Well, that's what we're getting at here. As this time interval gets closer and closer, you're looking at an average velocity, but over a smaller and smaller and smaller time interval. So small that eventually your speed would not be changing over that time interval, and you're basically calculating what the speed is, or in this case, what the velocity is at that instant. The closer t2 gets to t1, the closer you are actually determining the speed at the time t1. That's what we call the instantaneous velocity. So we will actually use this as a definition. Our instantaneous velocity, which I'll now just write as v without any subscript. So v, the instantaneous velocity, is equal to the average velocity at some point as the time interval goes to 0. In other words, as t2 gets closer and closer and closer to t1, as the final time gets closer and closer to the initial time, the slope here will get closer and closer to the slope right at t1. In other words, the slope of a tangent to the curve at t1, which we could write mathematically as the limit of v average as delta t goes to 0. Or the limit as delta t goes to 0 of v average, which is delta x over delta t, so that the deltas, the change in t and the change in x, get smaller and smaller, and eventually they become infinitesimally small, which we then write as dx over dt. And hopefully you recognize that as a derivative, the first time derivative of position. So what we have is that the instantaneous velocity of the object as it moves is the first derivative of the position, dx over dt, which then comes from this limit of the average velocity as the time interval goes to 0. All right, let's try this. Let's stick some numbers in here and see how it works out.